Today you will be solving exponential equations. So an equation such that a equals b to the cx power, where the exponent includes a variable, is an exponential equation. So for example, if we have something like 16 to the power of 3x equals 18, that's an example of an exponential equation. So our steps to solving these are fairly simple. If possible, we want to rewrite both terms so that they have a common base. Once the bases are the same, we can actually equate the exponents, and then we're going to solve and check for extraneous solutions. So if we look at this first example, 256, if off to the side, we do a factor tree for 256. We know 256, let's try dividing it by 4. It does end up being 4 and 64, and 4 breaks down to 4 and 16, or 4 and 4. Well, 64, we know breaks into either 8s or 4s. We've already broken it down to 4 and 16. So what we can do now is we can write 256, see how there's 1, 2, 3, 4 4s. We can say that's 4 to the 4th power, to the 2x power, because we still have 2x power, equals, we have 3 4s for 64, 4 cubed. So now that our bases are the same, they're in base 4, we can equate the exponents. So 4 times 2x equals 3, or 8x equals 3, and x equals 3 over 8. That's it. That's all you got to do. Take a minute and try the example you tried. Hopefully you found x to be 4 over 9. Now let's look at another type of problem. Same kind of situation for 8. If we were to do a factor tree for 8, we know that's 2 and 4 breaks into 2s. So we can write 8 as 2 to the power of 3, and this is all raised to the x power. We know the square root of 4 is 2, so we can say that's like 1 over 2, or 2 to the 3rd power to the x power is equal to 2 to the negative 1. Remember, when you have a negative exponent, it flips whatever the base is to the denominator of a fraction. So now that our bases are the same, we can equate the exponents. So 3x equals negative 1, or x equals negative 1 over 3. Take a minute and try the example you tried. And hopefully you found x to be negative 1/2. If we look at how we would do logarithms with different bases, we have this thing called the change of base formula. And for any positive numbers, m, n, and c, where b and c are both not equal to 1, notice we have the base of the logarithm, right? And here we go. So it's essentially like you can do log base 10 or log base e, because I know I have a calculator button for that. So if I do log of the large number over log of the small number, we get actually log base 7 of 14. And it's really that simple. If we look at this next type of problem, to find the value of the expression, we're going to do log of the large number, which in this case is 111, over log of the base of the original log, which is log 9. And then we just type that into the calculator, round to 3 decimal places, and it does end up being 2.143. If we look at the next example, we'll do log of the large number, 36, over log of the base of the original log, 216. And this ends up being 0.66, repeating 0.6667, or you can also say 2/3. I want you to take a minute and try the 2 example you trace. And hopefully you found for A, log base 8 of 32 is around 1.667, and for letter B, log of base 4 of 18 around 2.085. If we look at our next type of problem, notice we have 6 to the power 4x equals 512. Well, if we were to do a factor tree for 512, notice that everything breaks into base 2. But if we look at 6, I only have 2 and 3, so there's no way for us to break it down to the same base. So the question becomes, well, what do we do? Well, to get rid of the 6 to the 4x power, or to make the 4x become small, remember one of our log properties we talked about earlier, we can log base of the power. So if the base of the power is 6, I can do log base 6 on both sides of the equation. Okay, once we do that, now we can solve for x. So we know on the left side, it's like the log base 6 of the big 6 cancels out, and we're left with 4x equals log base 6 of 512. Okay, or x is equal to log base 6 of 512 all over 4. Now, to find out what the approximation is, we just use that change of base. So what we'll do is we'll do log 512 over log 4, or log 6, excuse me. And then I'm going to push enter on my calculator, and then I'm going to push divide by 4. And it should give you a decimal approximation of 0.870. And that's it. So you can give me this answer. Okay, so now what I would like you to do is to try the example you try. And hopefully your final answer, you do get x equals log base 5 of 130 divided by 2. When you type that into a calculator, you should have log of 130 divided by log 5, push enter, and then push divide by 2. We will also look at problems with e, which remember is Euler's number. It is an irrational number like pi. It is has a base natural log is e. Okay, so the first thing we're going to do is we are going to isolate the e. So in order to do so in a, we're going to divide both sides of our equation by 5. So we'll have e to the negative 3x equals 9. Now, we're going to ask ourselves in our minds, what has base e? Okay, well, what has base e is natural log. So what we'll actually do now is we'll natural log both sides of our equation. So after we have done that, notice the natural log of e is just 1. So we're left with negative 3x equals the natural log of 9, or x equals natural log of 9 all over negative 3. And from there, you can just type that in exactly like you see in a calculator, and it should give you approximately negative 0.732. Okay, let's look at another one. Same steps here. We want to know, how are we going to isolate the e? Well, hopefully we recognize we're going to add 8 first. So we'll drop the 2e to the 5x equals 38. Now to get the e alone, we'll divide both sides by 2. So e to the 5x equals 19. Now again, what has base e? Natural log does. So we'll natural log both sides. The left side becomes 5x, and the right side becomes natural log of 19. We're going to divide both sides by 5, and we'll get x equals natural log of 19 all over 5. And when you type that into a calculator, exactly like you see, it is about 0.589. And that's all you got to do. Now I would like you to take a minute and try the example you tried. Hopefully with this one, you recognize the e is already isolated, so you can go ahead and natural log both sides. When you do so and you subtract 3, you do get x equals negative 3 plus natural log of 24. And when you type that into a calculator, exactly like you see, you do get around 0.178. For our next type of problem, now we're going to look at factoring equations that have multiple e's. So whenever I see something like this, sometimes it kind of really stresses me out. So if I can relate it to something that we've done in the past, win-win. So if we look over in the thinking bubble, can't we think about it as x squared minus 4x plus 3? Well, we know that factors to x minus 1, x minus 3. Okay, so same similar thinking process. we know we're going to have our -1 and -3. But instead of an x and an x, we're going to have an e to the x and e to the x. Okay, and then just how we solve by factoring, we set each factored piece equal to 0. We will do the same thing here. We'll say e to the x minus 1 equals 0 and e to the x minus 3 equal to 0. And we solve each baby equation. When we add 1, we have e to the x equals 1. And in the other equation, when we add 3, we have e to the x equals 3. Now, what has base e again? Natural log. So we know we'll have natural log of e to the x equals natural log of 1. Natural log e to the x equals natural log 3. So we'll have x equals the natural log of 1, which hopefully you remember from last time to be 0. And we'll have x equals natural log 3, which you can leave that way or you can give me the decimal approximation. If I type natural log 3 in a calculator, it does give me 1.099. And that's all we do. Now I would like you to take a minute and try a similar problem. Hopefully you found for this one, it factors to e to the x minus 1 times e to the x minus 7. And you do get x equals 0 and x equals natural log 7, or approximately 1.946. Let's look at one more type of problem. So same kind of thinking process that we did earlier. So I want you to think of this in regards as x squared plus x minus 2 equal to 0. It's like I'm going to ignore these base 3's. Okay. Now, factors of -2 that add to give me +1. Well, +2 minus 1. When I do +2x minus 1x, we do get the middle 1x. So I'm going to think of something very similar for this one. But instead of using only a base of x, we're going to use a 3 to the x. Okay, so 3 to the x, and we're just going to input our +2 and then -1. Now, just like we did before, we're going to set each factored piece equal to 0. Okay, so well, 3 to the x equals -2, and 3 to the x equals 1. Now, in order for us to get this to work, we have to do log of the base of whatever we're raising to the power. So log base 3 of 3 to the x equals log base 3 of -2. And the same thing in the other equation. Log base 3 of 3 to the x equals log base 3 of 1. Well, we can't do a negative log, so right away we know this guy is out. Here we'll get x is equal to log base 3 of 1, which, if I move the equals x to this side and then write it in exponential form, 3 to what power equals 1? Well, it's just 0. That's it. Take a minute and try this last problem. So hopefully you find the only solution for this one is x equals log base 4 of 5, or approximately 1.61. Yay, time to practice. The end.